Hello everyone, welcome to Blitz Audios. And today we'll be looking at the mind map of the chapter Electrostatic Potential and Capacitance. This is the second chapter in the physics syllabus of grade 12 Cbse. Mind maps are a great way to revise chapters in a fast manner. These are effective during last-minute revisions for your grade 12 board exams. Now, this is the mind map that we're going to be using here. As you can see, it's very extensive and contains a lot of data. Therefore, we have divided this mind map into 4 sections and we'll do a brief explanation of each segment. Let's begin, shall we? So, our chapter is Electrostatic Potential and Capacitance. So firstly, we'll be learning about electric potential. What is electric potential? Electric potential is defined as the work done per unit test charge by an external agent in moving the test charge from reference point to the desired point. The SI unit of electric potential is joule per coulomb. And its formula is V naught is equal to work done divided by charge. V naught is for electric potential. So when you have a test charge here, which is present in an electric field, it experiences some force, whether attractive or repulsive. And that work done by this electric field or other external agent is known as the electric potential. Now, in grade 12, we'll be learning different kinds of electric potential. And in these parts, the main thing that differs is the source of the external agent. What type of external agent is used? Firstly, we study the electric potential due to a point charge. So if you have a test charge here, small q, and we have a charge capital Q here, which is a point charge, then both of these repel if they have the same charge, or attract when they have the opposite charge. And that can be positive or negative, or a combination of both. So the electric potential on the test charge due to the point charge, capital Q, is given as Vp is equal to Q divided by 4 pi epsilon naught R. Now, there are a lot of symbols here and we need to find out which is which. Vp stands for electric potential due to point charge. Q stands for the point charge, the quantity of the point charge in coulombs. Pi is a constant whose value is equal to 3.14. Epsilon naught is a constant which will recurringly occur in this chapter and in further studies of electricity. And it's known as the permittivity of free space. So the permittivity of free space. So the ease with which an electron moves through free space is known as permittivity of free space. Permittivity is different for different materials. So E naught refers to permittivity of free space, such as vacuum or air. And R stands for the distance between the point charge capital Q and the test charge small q. Let's look at the next scenario. Electric potential due to a system of charges. So over here, instead of one charge, capital Q, we have small charges such as Q1, Q2, Q3, and then we have a test charge, capital Q. So what is the electric potential experienced by this charge Q? It is given as V is equal to 1 by 4 pi epsilon naught sigma Qi by Ri. So what does this mean? Pi is the constant 3.14, epsilon naught is permittivity of free space, sigma stands for summation. So if you have two charges present, this value will be Q1 by R1 plus Q2 by R2. And for 3, it will be Q1 by R1 plus Q2 by R2 plus Q3 by R3. So the I here represents any value from 1 to n, where n is the maximum number of charges present in the system. The third type of electric potential is potential due to a dipole. What is a dipole? A dipole is any substance which has both positive and negative charges which are separated, and the net charge of this dipole is 0. The potential due to a dipole is given by V is equal to 1 by 4 pi epsilon naught P cos theta divided by R square, where P is Q into D. Q is the charge and D is the distance. Cos theta is the angle between the displacement between the point charge and the dipole itself. And so in this figure, which is given, theta is equal to angle AON, this angle. So when theta is equal to 0, this point would be in the same line as that of the dipole. So if A was here, then theta would be equal to 0. And when theta is equal to 0, the value of cos theta is maximum. So V will be equal to 1 by 4 pi epsilon naught P by R square. This is also known as potential due to a dipole in axial position, because it's at the same axis as the dipole. What happens when theta is equal to 90 degrees? When theta is equal to 90 degrees, cos 90 becomes 0. So the whole value of the electric potential due to a dipole becomes 0. And this scenario is known as the equatorial position of potential due to a dipole. Another thing to note is about the famous scientist Alessandro Volta. Now, it's from this scientist that the name volt appeared. And this volt is the SI unit of potential difference. So in 1774, Alessandro Volta wrote a treatise on the forces of attraction of electric fire, which is later known as electricity. So what he theorized was, if there are two charges and there is a wet medium in between, charge will conduct through. And this is found in the introduction of your chapter, Electrostatic Potential and Capacitance. From 1, we move on to 2. Now, an important topic in the study of electrostatic potential and capacitance is what is known as the equipotential surface. Now, to better understand an equipotential surface, let's draw some figures. So this is an electric field. Excuse me for my drawing, it's pretty bad. And these are surfaces on the electric field. And let's have a point charge Q here. And let's have circular surfaces and radially outward fields. What is known as the equipotential surface? An equipotential surface is the surface where the electric potential is same at all the points of the surface. So if we take this surface A, you keep a charge Q here and then move it to here. The electric potential stays the same. There is no difference in the value of electric potential. Equipotential surface is the component of electric field parallel to an equipotential surface is 0. So what the statement says is that if there is a component of an electric field which is parallel to an equipotential surface like this, then that component is 0. So what it also says is that the electric field is always perpendicular to equipotential surfaces in electrostatics. Another thing to note is that since the electric potential stays the same across an equipotential surface, the work done on an equipotential surface is absolute 0. There is no work done. From equipotential surfaces, let's move on to electric potential energy. According to our textbook, electric potential energy is referred to as the negative of work done by the electric force. The work done is equal to K, which is the constant 1 by 4 pi epsilon naught Q by R. And electric potential energy, which is represented by U, is minus W, where W is the work done. So electric potential energy is the negative of work done by the electric force as the configuration of the system changes. The formula used to find out electric potential energy is UR2 minus UR1 is equal to minus W, which is equal to Q1 into Q2 divided by 4 pi epsilon naught in brackets 1 by R2 minus 1 by R1. Now, UR2 is the electric potential energy at the position R2, and UR1 is the electric potential energy at the position R1. So this whole value refers to delta U, or difference between electric potential energies. Minus W is the work done. So as we've stated earlier, electric potential energy is the negative of the work done. Let's look at this formula. Q1 is the charge on the position R1, and Q2 is the charge on the position R2. 4 pi epsilon naught is the constant, where epsilon naught is permittivity of free space. Pi is equal to 3.14. And R2 is the position, and R1 is also a position. So R1 is initial position, and R2 is the final position. So the system of charges Q1 into Q2 is transferred from R1 to R2. So to find the electric potential energy, we subtract the values of work done at R2 and R1, and upon further simplification, we arrive at this formula. Now, if the separation between the charges Q1 and Q2 is R, then electric potential energy due to distance R will be equal to Q1 into Q2 divided by 4 pi epsilon naught R. So if this value becomes 1 by R, then the formula gets simplified to this. Another way of calculating potential difference is to use the electric potential energy. So the formula given here is VB minus VA is equal to UB minus UA divided by Q. UB minus UA, also represented as delta U, is the change in potential energy. And Q is the test charge which is used to find out electric potential energy. It is important to note that in most experiments, the test charge is unity. VB minus VA is delta V, which is potential difference. Now this is due to point charges, Q1 and Q2. What happens when we have to find the potential energy due to a dipole, which has its positive and negative charges separated, but the total charge is 0? The formula used to find the potential energy at any point due to an electric dipole is du is equal to P into E sine theta d theta. So theta would be the angle between the displacement between the dipole and the point with respect to the axis of the dipole. P stands for dipole moment, and which also is equal to 2qa or qd, as we saw previously. And sine theta is the sine of this angle theta, and d theta is due to the torque which was used to get this formula. So the differentiation of all these formulas will be found in your textbooks, and this video is primarily devoted to application of the problems. So the formulas themselves are pretty important. If we choose the potential energy of a dipole to be 0, then the angle theta would be equal to 90 degrees. So due to standard conventions, we choose potential energy to be 0 when theta is equal to 90 degree. So then u theta, which is the final orientation, minus u90, which will be the initial orientation because we took this as 0, will be equal to the integral from 90 degrees to theta, dipole moment P into electric field intensity E. Sine theta is the sine of the angle, and d theta is the deviation of angle by a small amount. So u theta will be equal to minus PE cos theta. This is the final formula to find the potential energy due to a dipole. And since cos theta is present in the final formula, we can take it as a dot product, because the dot product of two vectors will have cos theta. Now this formula is applicable if it is rotated through an angle theta against the torque experienced by the point A. Let's move on to the third segment. Before moving any further towards capacitance and dielectrics, we need to know explicitly what are conductors and insulators. We have studied this in our previous years, but it is always good to refresh the concept. A conductor is such a material which, when placed in an electric field, the free electrons move in a direction opposite to the field. Suppose we have a conductor here, and there's an electric field E. Then the free electrons present would start move in the direction opposite to the direction of the electric field. Materials which exhibit this property are known as conductors. And conductors are the ones which have free electrons. They include metals, graphite, etc. What are insulators? Insulators are materials in which electrons are tightly bound, and when exposed in an electric field, the electrons do not move. That means that these substances have no free electrons. An example of an insulator is mica, rubber, air, etc. Now there are some properties with respect to an electric field and a conductor present in the electric field. The first thing is the electric field inside a conductor is always zero. The electric field is always perpendicular to the charged surface. So to find the electric field here, it always is perpendicular to this surface. If it wasn't perpendicular, then it would have a component E cos theta, which tends the charge to accelerate, which creates surface current. But the problem with surface current is it simply does not exist when we study electrostatics. So the angle between the electric field due to the charged surface and the charged surface itself is always 90 degrees. In static state, there will be no additional charge in a conductor. In later chapters of magnetism, you would know that when a current is moved through an electric field, it generates current. But if the current is static or stationary, like this one, then there is no additional charge produced. Let's move on to a term known as dielectric. What are dielectrics? A dielectric is an electrical insulator that can be polarized by an applied electric field. So suppose we have a dielectric here, and we have an electric field which passes through this dielectric, then it attains a temporary dipole moment, which means that the positive center and negative centers of the molecules inside the dielectric would shift apart. Materials which exhibit this property are known as dielectrics, and they can be polar, which means having a permanent dipole moment and which experiences torque due to the electric field, or non-polar. Materials which do not have a permanent dipole moment, which separate their positive and negative centers due to the electric field. Let's move on to the last segment, which deals with the topic capacitance. Now, what is capacitance? Capacitance is the measure of the ability of a dielectric to store charge. And the general formula given for capacitance is C, which stands for capacitance, is equal to Q, the charge, divided by V, the potential difference. Capacitance of a parallel plate capacitor, C is equal to K E naught A by D. K is dielectric constant. So what it means is that suppose we have two plates present and a dielectric material is kept here. The capacitance produced by this setup, known as parallel plate capacitor, is K E naught A by D. The K here is dielectric constant. E naught is permittivity of free space. A is the area. Okay, let me write it out here. A is the area of the plates. And D stands for the distance between the plates. So to find the capacitance of a parallel plate capacitor, we multiply the dielectric constant with the permittivity of free space with the area of the plates of a parallel plate capacitor and divide it by the distance between the plates of a parallel plate capacitor. This will give us the capacitance of this device. Capacitors are usually used in many electronic instruments to store charge. Now, there's one type of parallel plate of capacitor which is known as the parallel plate capacitor, and it is in this setup. There is also another kind of capacitor known as the spherical capacitor, which consists of a spherical surface at the center of which there's a charge Q. So the capacitance of a spherical capacitor is C is equal to 4 pi epsilon naught, and in brackets 1 by R1 minus 1 by R2. So it's 1 by 4 pi epsilon naught, and then 1 by R1 minus 1 by R2. So this is for a spherical capacitor. What happens when we have an isolated sphere as a spherical capacitor? So that means there's only one sphere in this situation and a charge Q. So C will be equal to 4 pi epsilon naught R. Capacitance in a spherical capacitor is always present at the surface. And for highly advanced capacitors, it will be in this area, the area between the volume. Actually, it's not the area, it's the volume between the two spheres. Next, we will move on to finding energy stored in a capacitor. The reason we find this is to justify the application of capacitors. Capacitors are used to store charge, and they store energy as well. So the energy stored in a capacitor is U is equal to half Cv square, or which is also equal to Q square divided by C. So here C stands for the capacitance, Q stands for charge, and V stands for potential difference. Using the formula U is equal to Q square by C, we also get the formula U is equal to half QV. Now, in practical life, the energy stored in any electronic device is not using a single capacitor. Capacitors, when combined, show unique properties. As with resistors, which you studied in class 10, capacitors can be combined in series or in parallel. In series, two capacitors would be like this, and in parallel, they would be like this. Excuse my drawing. Now, this symbol, where both these lines, parallel lines, are in the same length, is the symbol for a capacitor. Now, in series grouping of capacitors, the charge Q is constant. So, to find capacitance, we use the formula. To find the energy stored, we use the formula U is equal to Q square by C. So Q square by C becomes Q square by C1 plus Q square by C2 plus Q square by C3 up to Q square by Cn. So the series grouping of capacitors has the final formula 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus up to 1 by Cn. So for two capacitors, 1 by C will be equal to 1 by C1 plus 1 by C2, which on further calculations you will get C is equal to C1 C2 divided by C1 plus C2. However, What is the scenario in the parallel grouping of capacitors? In the parallel grouping of capacitors, the potential difference is the same as they're connected in parallel. Therefore, CV square is equal to C1V square plus blah, 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 which gives us the final formula. C is equal to C1 plus C2 plus C3 plus etc. up to Cn. And for two capacitors, C is equal to C1 plus C2. And that finishes the chapter Electrostatic Potential and Capacitance. We learned about potential, capacitance, and devices associated with them. Did you know that our channel, Brain Blitz Audios, specializes in providing free education to all? To be a part of our journey, please subscribe to our channel. Thank you for watching this episode of Mind Maps Class 12. Until next time, goodbye.